Okay. Okay, now what time does your watch say? 1. Okay, so let me get started. My name is Steve Skiena, and this is CSE 373, the Analysis of Algorithms course. And let me start off, I guess, by reviewing the basic course mechanics. Again, this is a course 373. It's a course on algorithms. There are, first of all, okay, let me just take it. First of all, everybody should get copies of the syllabus and the daily problems. These are handouts in the back. If you didn't get it already, you can pick it up later. Okay? Let me start off actually first, just to make it a little bit easier in the course mechanics. I'd like to introduce our course TA, at least for the moment. Okay? This is Jake Christensen. Everybody give him a round of applause. Okay. Now, I have taught algorithms, for 20 times already. This class, by far, is the largest offering I have ever had. Okay, I have never taught to more than 120 students. The room capacity is limited to 210 students. Okay, I always have graduate TAs. As of the moment, I don't have any graduate TAs. So Jake has volunteered to grade all of your homeworks and exams and everything like that. That is fiction, okay? He is, he's an undergrad TA. He is going to be helping helping you guys if you have questions. He's going to help run what is hopefully going to be the discussion board on Piazza and things like that. But recognize that we have a TA situation which is going to motivate some of the other issues in the course. But for now, this is Jake. He's got office hours that are listed on the website. I believe it's Wednesdays. Thursdays. It's Wednesdays at like 4 o'clock. And you're going to be there, right? Yeah, okay. So then there's no problem, okay? Give him a round of applause and let him get to his class. Okay, thank you. Okay, so let me go through that. That's kind of an important introduction because, again, we do have some issues here in this class. But let me first do the standard mechanics and stuff like that. First of all, the prerequisite for this course, there are 2 prerequisites for the course. There's a data structures prerequisite, meaning you've taken the equivalent of CSE 214, okay? And you've had some kind of mathematical maturity as reflected by the linear algebra prerequisite. Why do these prerequisites? It's because you're supposed to take them before you take the class. Does everybody get that idea? How many people here are registered but do not have the prerequisites? Okay. How many of you are lying at that point? Okay. For some of you, again, if you don't have the prerequisites, sometimes people can, hopefully the registration system blocked you. But if not, it is a bad thing to take the course without the prerequisites. Algorithms tends to be a hard subject. It's important to have a background in data structures. It's important to have some level of maturity here, mathematical maturity. And so if you do not have the prerequisites and somehow manage to register, I would encourage you to take it another semester. Okay? That's why we have prerequisites. The students who have the prerequisites don't do as well. Any questions? Okay, how many people here are not registered but would like to be registered? Okay, hopefully a very small number. Again, as of now, as far as I know, there are no seats. The capacity of the room is the limiting constraint. If spots become available, you guys could look. Some of the people I'm sure in here, somebody will decide to drop it or something like that. So try to keep your eyes open, but at the moment I have no power to let anybody in. If you've got an incredible sad story that I need to know about, okay, you can come and talk to me about it after class. But at the moment I don't really have power. Okay, any questions? Okay, good. Okay, so let's go through. What I'd like to do now is to go through, first of all, this is the textbook for the course. I think it's a very good book, okay? And there are people in the world who agree with me. So that this is a book that supposedly, when you interview at Google, Google very nicely sends you an email saying, to prepare for your interview, you should read Skiena's book. So which I think is very nice of them. And so we're going to use this as the textbook. Again, I follow it fairly closely in my lectures, but I strongly encourage people read it. Algorithms is a hard thing, and reading and thinking deeply about things is an important aspect of this. I personally think it's a lot easier to get something, read something on a paper book than it is on an electronic version. When you open up my algorithms book, what do you see when you open my algorithms book? You see algorithms. When you open up your laptop computer, what do you see? Facebook or something like that, okay? So I do recommend reading the book, and however you read it is up to you, okay? The grading in here, we're going to have the following grading scheme. I'm now going to go through basically what's on the syllabus. But on the grading, the bulk of the grades in here are going to come from the midterms and finals. There's 2 midterms, there's a final. I'm weighting them equally this year, but that's going to account for the vast bulk of your grade in here. So you need to do well on the exams. There are going to be 5 homework assignments that are going to be given. The total weight for the homework assignments is 15%. These I allow and encourage people to work on in pairs. These are paper assignments, historically paper assignments. And I think that understanding algorithms and learning the material, a lot of it is, you have algorithm problems, and there's kind of a flash of insight you need to sort of solve these things. And the way you get that flash of insight is by beating on the problems for a long time. So, and often to discuss it with somebody else. So I encourage people to do the homework assignments in pairs so that you have someone to discuss it with. That doesn't mean divide the problems in half and each of you do half. That doesn't do anybody any good, okay? Or does each of you half good, okay? But how well you think about and do the homework assignments has a lot to do with how you're going to do on the exams, okay? Any questions about that? Okay. Don't know. Okay. Is anybody doing anything? Is there somebody on back leaning in a bad way? Okay, so don't do that. Okay? That's considered a bad thing. Okay? Okay. What else should I want to tell you? Of the 5 homeworks, one of them is not going to be done in pairs. Homework 4 is a problem where there's going to be a programming problem where your grade's going to be based on how fast your algorithm is. The winner, the fastest algorithm, wins a prize. The slowest algorithm also wins a prize, but you don't want that. Okay, what else do I want to say? On my exams, the way I usually do my exams is I draw problems from the book, okay? Usually, mostly, not always, not going to promise it. But an excellent way to study for the exam is going to be to review what is on the, to look at the problems that are in the homework part of the book. Not only just the homework assignments, but if you want more practice, and I think it's a good thing, going through other problems in the back of the book is an excellent thing to do. Okay, so if you say, how do I prepare for my exam? That is what I usually tell people. Look through the books. I mean, obviously, stuff you don't understand, read in the book to understand how you can solve it. But then go back, and I think the more practice you get, the better off you are. Any questions? Now, because we have a much larger class than usual and likely less TA support than usual, we're going to be doing 2 things a little differently this year. One is that I'm going to be grading the homework assignments by peer grading. Actually, I'm not saying I'm going to grade it. You're grading the homework assignments by peer grading. So we are going to set something up where over Solar, over the I guess it's Blackboard, there is, you will all each be assigned for every homework 3 homeworks to grade, 3 other students' homeworks to grade. And, your job is you will get an answer key, you will grade them, you will assign them scores, and that's how we're going to grade the homeworks. Now, my belief is it's actually going to be an educational thing to look at other people's things. A large part of understanding when an algorithm is right is, to a certain extent, seeing when it's wrong or seeing what other alternatives there are. And so I believe this is going to be an informative thing on the scale of about grading 3 assignments per person each time, okay? And that will force you to look at the answer key, that will force you to do some of these other things. 5% of the grade that we're going to be giving in the course is going to be the response that you get to grading them, okay? Any questions about that? So I want to make sure you did your home grading assignments, make sure that it's on the up and up. Yes? Okay, so what should you do if someone gives you all zeros? I'm going to give you what is the honest best thing to do, which is to do nothing. Okay, and let me explain why. Okay, if the homework is 5%, 15% for the semester, okay, divided by 5 homework assignments, how much is each homework worth? 3%. Okay. Likely they're not going to give you all zeros on all problems, okay? And if so, there's going to hopefully be 3 people who are grading it, and the average or the median or something like that will raise it. A small misgrading on a homework assignment will do very, very little harm to you, or essentially no harm to you. And the right thing to do is to realize that what matters is that you understand the material, and that matters is how you do on the midterms. This is this is my honest belief, okay? And that the time that you're going to spend fussing about the homework most likely is better spent with the book open and trying to do better on the next thing. That's my honest belief. Now, some of you may not be happy with that. If you're not happy with that, okay, you can talk to the TAs and we'll see what happens, okay? But intellectually recognize that in this course, we're going to spend a lot of time talking about asymptotics, big O, okay? Big O of your grade is what you do on the midterms and final, right? How do you do well on the midterm and final? Well, you will learn the material by doing the homeworks, okay? And that the residual scores on these other things aren't so important, okay? That's I guess, the answer that I'd like to give. Any questions about that? Okay? So we're going to try that as an experiment, and we're going to see what happens. Okay, what else is there? The other response that I'm going to do as an experiment this year, because the class is large and the TA thing is small, I'm going to experiment, I intend to experiment, where on the midterms, I am, and presumably the final, I'm going to make half the questions multiple choice. This is going to be an experiment, okay? And I'm going to then be doing a correlation study at the end of the semester to see how the multiple choice things did with the other problems. In general, I expect it to probably be pretty good. So that hopefully you will be seeing, and you'll be a little bit of a guinea pig on it. But I want to see how that works out, okay? Any questions about that? Okay? But again, I'm doing this with trepidation because I do think that the way that you figure out algorithms is about finding a way of doing things. And that's something that's not easily reduced to a memorization or multiple choice thing. And so we'll have to see how well that correlates and how that works out. Any questions? For now, don't worry about it. Study it the same way. That's my plan for the way that this is going to work. Any questions? Okay, good. What else can I say? If I go through the syllabus. One thing I do want to say is that my midterms and my exams are designed to be hard, okay? That means that, and when we grade these things, historically, the average for my midterms is usually in the 60s, often in the low 60s. Now, I curve this, okay? And the median, when I come up with my final semester grades, I give, the median is basically a B minus. So what does it mean if you get in the 60s on the median of a if you get, let's say the median or the average is around 63 on my midterm. What grade does that correspond to? I didn't hear you say that. Are you failing the course? Okay. What if you got a tiny bit below it? Are you failing the course? Okay. So again, I want people to be worrying about what their grades are. I do want people to be, care about what their grades are. On the other hand, I want there to be a healthy level of concern. There's 2 types of students that are sort of get into problems, or not in problems, but that I sometimes have to deal with. One are the students who will get in the 30s on the midterm. Is that person failing? Okay, should that person be concerned? Do I see these students ever? No. Okay. Okay. Now, I worry about those, and there's sometimes people who will get in the median average, suddenly feel they're doing so terrible, and threaten to drop the course because, oh my God, I'm failing. Recognize I am going to curve it. Recognize that the median is going to be hard. Recognize when you walked out of here, you didn't get all the problems, but neither did almost anybody else. The high grade usually, by the way, is in the 90s on my exams, okay? So, I mean, there are people who do this. I'm not trying to say this is a superhuman thing, but the tests are designed to induce variation, because that's what I think is important in grading these things, okay? So keep that in mind when it comes to interpreting your performance on the midterms. Any questions? Okay, good. I am hoping that these lectures are being recorded by the Echo 360 thing. And so if so, they are on, will be available on Blackboard. If anybody, when anybody first sees a lecture, this thing recorded, send me mail just so I know that it's there. Okay, I kind of like to make sure that they're really doing it. Okay, and so let me know that. What else can I say? The webpage for the course. Oh, I've taught this course in past semesters, and my lectures are available on video, on YouTube, and and some other websites. If you want, you can look there, although I am changing the lectures a little bit this year. I am trying to make more so than I usually do. But I am going, so I encourage you, but anyway, you're paying for a live performance, so I do want you to come to class, okay? Any questions? And in fact, one way that I encourage coming to class that's very important is the daily problem. So what I have done, my second assignment sheet that I gave you out here is a list of daily homework problems. What is the purpose of the daily homework problem? The daily homework problem is, starting next class, at the beginning of class, I'm going to go work out a solution to a particular problem, okay? And, but before the class, at the beginning of class, I will be collecting, because they will be deposited here, printouts of not printouts, a paper with your solution on it, one side of a sheet of paper. I want people to look at the daily problems before I go and do them in class. Because again, a lot of the way you learn algorithms is you think about a problem, you get stuck, my God, what's he trying to say? And then you see how it's done, and then it makes sense. Okay, it's one of these things that if you don't put the thinking into it, you don't see where the traps are that you fall and then where you get stuck. And so what we will do with the daily problems are that I collect them at the beginning of class. We are not going to grade these daily problems. We will count them. And then at the end, 5% of your grade will be the count of how many daily problems we have for you each class, over the course of the semester. Now, at the moment I start class, I cover up, I take all of these problems, and there's no more daily problem turned in. It's got to be turned in before class, before I decide to do anything about it. Okay? If you don't get your daily problem in on time, is it a big problem? It is 1/26 of 5% of a class where 75% of the grade is the midterms and finals, right? So don't worry about that. This may take some programming for you guys to not worry about it. But understand that what I'm saying is true. Okay? Any questions about that? Yes? You have to be here on time. You have to be here on time to be on time. Okay, I guess is the way to put it. Okay? So, when you say you're on time is a particular moment in time. Okay? And, that moment of being on time has to be here. Okay? And then you slither back to your seat. Okay? Any questions? Okay? Why do I do this? One, I encourage it. It encourages people to come to class, which I think is a very good thing. But more important, I think that it's also, again, thinking about these problems and working through seeing why there is a solution is important. Once you've thought about it, then you can appreciate it. And if I'm just lecturing on it, you can't appreciate it. Any questions? Yes? The lectures are theoretically, presumably, being recorded by, I assume, that sensing device up there. If so, they should be posted onto the the solar system channel and stuff like that, Echo 360. People have seen these lectures before, right? So let me know when you see evidence that they are in fact recording this thing. Okay? I believe they are, but until I hear a problem, I need to know. Any questions? Okay, what else can I say about this? Again, I encourage people to work in partners on the homework. Try to find a homework partner you know and like in the class. If you can't find a partner, I will randomly hook you up with somebody else who can't find a partner. I do not want to be a marriage counselor, okay? So in other words, I don't want to hear anything about how bad a louse your partner was. What is going to happen to your partner if you do all the homework problems and they just sign their name to it? What's going to happen to this person? They will fail the exams, and you will get your rewards then, okay? If you find that you don't enjoy working with this person, you can break up and find another partner, okay? Is that clear? Okay. Now, because we are going to be doing these problems remotely, through, hopefully, if there's a God, with this peer grading thing, you are going to have to scan your thing and upload it. And once we figure out the mechanics of this, we will give you instructions, presumably on the web page. Any questions about that? Okay. It doesn't mean that you have to typeset it, but it does mean there has to be a file for this. Okay. Any questions? Okay. What else would I like to say here? Talk about daily problems. Okay. One thing that I do have is there is on my website, algorist.com, there is a problem wiki where I let people, sort of post, or had a blackboard where people could solve problems on algorithm from my book and post solutions and stuff like that. Now, I have never looked at this algorithm wiki. Are any of the answers on that algorithm wiki right? I have no idea. Okay? Should you trust them? Probably not. Okay? But if you need that as a resource, you can do that. That said, I think that the way that you learn to solve algorithm problems is not by trying to copy or Google. This doesn't help, especially during the midterms. Okay? The way that you learn to do these things is by beating your head against them and finding the way of thinking. Again, solving algorithm problems is about finding a way of thinking. And that's kind of, you miss the point if you're resorting to a solution or something like that. Any questions? Okay, talking to TAs for hints, coming to see me, these are good things. Any questions? Yes?
The daily homework problems, those are problems from the textbook.
Most of them I think, are from the textbook. If you look at the printout here, they are, some of them I have typeset, so for some reason I may not have put down, either didn't know the problem number or maybe they're not in there. But presumably they're in the book, yes. Any questions? Okay, at least they're in the book with very few, if any, exceptions. Okay, what else do I know? There's some other boilerplates that I want to say here. If you have any kind of a learning disability or disability of some form, you should be registered at Disabled Student Services. I once had a student in my class who, midway through the semester, told me he was deaf and didn't realize that there was a Disabled Student Services thing. So if you're like that, okay, be aware who these people are and deal with them as you need to deal with them. There is a thing about academic dishonesty. There's a standard academic dishonesty policy. In here, again, plagiarizing homeworks is a good way to get into trouble. A better way is by trying to copy off somebody's exams or trying to break in and get exams. When we catch somebody, I bring them up in here, and there have definitely been students over the years who have fallen victim to this policy. Any questions about that? Okay. One other thing that I would say is that, every once in a while something bad happens to people, and they say, oh, can I have an extension on the homework? I have a policy where I give everybody one free extension on a homework for up to a week without penalty. You don't have to tell me about it. You write on the assignment, this is my free extension. Okay? And that way, if your dog dies, if something bad happens, you get one of these things a semester, right? You don't get a second one for the semester. Is that clear? Should you use this on your first homework? No, you should not use it on your first homework, right? You ration it. A lot of people use it on the last homework when the life is very complicated and they want to get that thing done. Okay? Any questions about that? Okay? And if you have a partner and your partner has used, somehow they gets into a situation, each assignment can only, the assignment, don't get a partner who has used an extension when you haven't. Let's just put it that way, okay? Any questions? That's the question to ask these people. Are you going to do the work, and have you used your extension yet? Any questions? Yes?
So to be clear, the one extension is per person, even though the assignments are being turned in.
I'm going to probably say let's say per assignment, per person, per assignment. Let's use a minimalist thing. This is not meant to be how many times can I figure out how to use it, okay? The question is, if I get into trouble, okay, what can I do? Okay? Any questions? So a minimalist interpretation is what I want. Any questions? And again, finally, there is, again, I like to have, again, it's a big class. I can't talk to too many people at once, but I do try to have a couple of, twice this semester, I'm going to try to have a lunch where I go up pizza with the prof, where I will have a sign-up sheet out my door, and the first 10 people who sign up, I will have pizza with. We will do one probably in October and one probably in November, and I'll try to remember and to announce when I have the sign-up sheet on my door. And so hopefully I'll get to know you. I have office hours, and we'll see that. Any questions about course mechanics? Okay, if we look at the syllabus for the semester, actually, wait, this thing, right, now you guys wanted this lower. Am I right? Let's see. Boom. Is this better? Okay, let's try that. Okay, hopefully this is better. Okay, so what are we going to be doing? The introductory part of the semester, again, there's several chunks of stuff we're going to be doing. The introductory part of the semester is going to be, we're going to talk here about what our algorithms mean. We're going to talk about the big O notation. We're going to talk about logarithms and the mathematics we need. That's the introductory part. We're going to spend another little unit on reviewing data structures from CS 214. I don't know if it's reviewing, but at least understanding what we need to know about data structures. They're the tools to build bigger algorithms from. We're then going to have a unit on sorting. On sorting, and because sorting tends to be a good way to introduce a lot of the basic ideas in algorithm. I know you've seen a lot of sorting algorithms over the years, but to get an idea of what the algorithms are, how they're analyzed, things like that, I think sorting is a very useful thing to talk about. And that will be basically what we will do up to midterm 1. Any questions? Now I want an honest answer, either hopefully by raising a hand to this, and if not, if you won't raise your hand, hopefully people will raise your hand. Right now the midterm is scheduled for what I believe is the second day of Rosh Hashanah. Does anybody have problems with that? There are a few people who have problems with that. If you have problems with that, send me mail, and we will see. We may end up, I haven't completely figured out whether it's going to be the day that I give it or the day after, okay? And send me mail if you have a problem with that. Okay? Any questions about that? Okay, so there's a chance I may end up slightly changing the schedule. If you look at the syllabus, you'll see that I have a Slack class scheduled for the 17th, November 17th, so I have room to slide something down. Okay, the next step is that we're going to have a big unit on graph algorithms. Okay, breadth first search, depth first search, minimum shortest paths, things like that. After that, we're going to have a short unit on combinatorial search. Okay, how do you backtracking? How do you search through all possibilities efficiently? And backtracking is going to be the subject of that contest homework 4 for the fastest algorithm that we're going to be talking about. After that, we talk about dynamic programming, which is one of my favorite subjects, although the students tend not to like it, okay? Dynamic programming is an algorithm design technique that once you understand it is amazingly easy. But unfortunately, until you understand it, it looks impossible. And hopefully, by the end of this, we will try to understand it. And after that is when we'll talk about midterm 2. Right now, as I have midterm 2 scheduled, it is going to be the Tuesday before Thanksgiving. Okay? And I think that that's a very good time for it. But I want to just take a look at this thing. Given a choice, if you had a choice, and I'm not giving you this choice, but I want to just get a sense of this. Okay, I think the best time for it is the Tuesday right before Thanksgiving. We might possibly have it the Thursday before that, okay? I mean, the earlier. Who here would prefer it to be the day I like, which is the Tuesday before Thanksgiving? Raise your hands. Okay, and how many people would prefer the day I don't like, which is Thursday before Thanksgiving? Okay, so it seems like all of us the majority of us share similar taste. This is what you should be expecting, that the Tuesday before Thanksgiving will be that. And then after Thanksgiving, we're going to talk about a topic that is very interesting, this whole notion of NP completeness. And when are there not efficient algorithms, and how can you tell? And that's usually a very interesting thing. Any questions? Okay, yes? Are the exams cumulative? The midterms are not cumulative. The final will be cumulative. Okay? Any questions? Any other questions about the mechanics in here? Okay, good. Okay, so let's now start talking about the course material. And so this is a course on algorithms. What is an algorithm? Okay? The phrase I like is someone described algorithms as being the ideas behind the computer program. Okay? It's the thing that sort of describes the procedure for solving a problem. You know about programs. You know what programs are. Somehow the algorithms are the thing that's not really the program, but somehow the method that underlies it. And for an algorithm to be interesting, it has to solve a well-defined, specified problem. Okay? And so, in some sense, the world of algorithms, at least as seen in this course, is in general a world of proving things. You want to have, here's a method, here's a problem, we want to solve this problem with an algorithm that always is correct and has a certain level of efficiency. In order for this to work, we need to be able to specify problems in a rigorous way. Okay? So, so here is an example of a famous algorithm problem, the problem of sorting. Algorithm problems are parameterized, if you wish, by a desired set of allowable inputs. Okay? In this case, for sorting, we're saying the input is a sequence of n numbers. Okay? And the output is going to be a reordering of the input sequence, a permutation, such that the ith element in the reordered sequence is before the I plus first element in the sorted, in the permuted sequence. Okay, so the first element is smaller than the second element, smaller than the third, ... Any questions about it? So the world of algorithms is going to rely on us specifying problems, precisely. They've got to have answers, okay? And we're going to be trying to design algorithms with the property that they are correct and efficient. Correct means that it gives you the right answer on every single input, okay? Efficient, well, talking about what exactly efficient means is maybe a more loaded question. But we're going to be measuring efficiency in here, generally using big O, worst case analysis, okay? And we want one that is going to, we're going to care here about algorithms that are good on large examples, not on ones that are small. We're interested in here on the fastest algorithm for sorting 1 billion things, not the fastest algorithm for sorting 100 things. Okay? And that's a consequence of worrying about our big O notation. Okay? Any questions? Now, the thing that makes it satisfying being an algorithm designer, again, I'm an algorithm designer. I don't do that much programming, frankly, these days. But when I design an algorithm, it doesn't matter what language it's on. It doesn't matter what machine it's on. Generally speaking, when we do this thing, there's a notion of an asymptotically faster algorithm. And a faster algorithm running on a slower machine is going to win over a slower algorithm running on a faster machine. Okay? And that's kind of one reason why we really care about algorithms and efficiency. Any questions? It's still maybe buzzwords. Now, correctness is kind of a, going to be my main lesson for today. Okay? That when we have an algorithm, if we have an algorithm problem, it specifies the input, it specifies the output. We say that an algorithm is correct if it is one that always, for every possible input, returns the correct possible output. What do we call an algorithm that usually returns the correct answer but doesn't return it always? What do we call that algorithm? We call it wrong. That's exactly what we call it. Okay? Now, sometimes there's technically a term called a heuristic people will sometimes use that says, oh, yeah, it usually kind of does well. And those things have their value, but not in this course. Okay? We're going to be interested in algorithms that solve the problem exactly. Okay? And that so somehow, for this to make sense, we need to have an algorithm problem that has a right answer. If you ask me, find the best tour for me to take between here and Brooklyn, okay, I can't answer that. Okay, what does best mean? Is it the one that's most scenic? Is it the one that is fastest? Is it the one that's the shortest distance? Okay, if you ask me which one is the shortest distance, that's now a well-defined algorithm problem. There is one shortest distance between where I am standing here and the Brooklyn Museum. Okay, and an algorithm problem, we seek a well-defined problem, and we're going to be worrying about proving, in some sense, convincing ourselves that the algorithm is correct in all cases. Any questions about that? Yes? Will we be concerned about rigorous proofs? So the answer is, when we say what is the difference between a rigorous proof and a proof, okay? This is a philosophical question. First of all, let's say a wrong proof, okay, could look very rigorous and have lots of statements in it. What's true is that algorithms are ideas behind programs. Proofs are ideas as to why something is correct, okay? And what is going to be important to see is you're going to need to have an idea when you have an algorithm. You're going to need to have a good, clear idea as to why your algorithm is correct, okay? That idea is usually best instantiated in a proof, okay? And so again, there's degrees of formality. When a proof is right or wrong, okay? A proof has an idea behind it. And it's sometimes people mistake, let's say, formality for ideas or something like that. You need to know why your algorithm is right, okay? If you have an algorithm and you don't know why it's right, what is your algorithm? Probably wrong. It's not necessarily wrong if you don't have a proof for it, right? But in my experience, these things often are, okay? Now, I tend to be, I won't say sloppier, but I tend to rely less on formal proofs in this class than many people who would teach it. But I don't want you to mistake the idea that it's not an important thing. There's an idea behind why algorithms are right and why they're wrong. And this is important. We're going to be talking about it. You have to understand this on an idea level. Any questions? Okay, so let's look at an algorithm problem and start to get a more concrete view of these kind of things. And this is a problem that I actually myself was once hired to work on. A problem related to robot tour optimization. There was this company that made robots for testing printed circuit boards. Okay, does anybody know what a printed circuit board is? You take your cell phone, you smash the case on the back of it. There will be this printed circuit board, right? That has wires and things on it that such that your components get soldered in, get placed in. There's a soldering iron that had to solder the joints of, the pins from the chips and things like that into the board. And you could imagine that if you had an assembly robot that had a, typical soldering robot, Okay, its job every day is to take iPhone printed circuits, or whatever device it's working with. The back of the board is going to have these holes where solder needs to go. And the robot's job is to move around, and whenever it has a point where it has to solder, puts down and applies heat and the lead gook to attach it to it, right? And so the robot has a job that is given a bunch of contact points on the back of the device, has to find an ordering to visit all of those points and solder, put down the solder to finish assembling the device. Does everybody kind of get that idea? So you can imagine, again, you've got, because you designed the iPhone, you know the geometric space where every one of these contact points is. Okay? Programming the assembly robot means finding and ordering of the points to visit. Every single iPhone that comes along, it's going to want to solder it in exactly the same way, right? What order does the robot want to work on, though? Would it be okay if the robot went beat, 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 beat? Would that be fine? Well, it would be fine, and that ultimately it would make the robot, it would make the phone, right? But what is the problem if it doesn't use the shortest possible ordering? What is the problem here? Yeah? The time is spent with these robots. These assembly robots are fast. You guys want to buy a lot of iPhones or something like that. To make these things quickly, you would like to find the ordering of these points that will minimize the total path length traveled. Does everybody get that idea? So once we believe this thing, then we can now talk about the robot tour optimization problem. Okay? Any questions about that? So how can we solve this problem? Let's try our little algorithm warm-up things. Suppose I give you a set of points. Suppose I want to find the order to visit all these points. Okay? Using the minimum amount of distance, how can I do it? Anybody have an idea for an algorithm? Okay, you. I could always brute force it. Okay? So one way to brute force it would be to try all possibilities, right? If I have n points here, how many possibilities are there? Okay? If you think about it, it's every permutation of visiting, how many ways are there to visit 3 points in a row? If the points were numbered 1, 2, and 3, I could visit 1, 2, 3. I could visit 1, 3, 2. I could visit 2, 1, 3. I could visit 2, 3, 1. I could visit 3, 1, 2. I could visit 3, 2, 1. In general, if I have n of these tours, the number of permutations I have, n points would be n factorial. And by the time you get to n equals 10 or 20, you will not be able to solve this in time proportion, any reasonable level of time. Okay? So we agree that if we try every possible tour and pick the minimum one, that one is going to be the best possible tour. Okay? But finding that is that's an n factorial problem that is bad. Can anybody come up with a faster way of doing it? Yes?
Short segments and then try to connect groups of short segments. So, for example, take a point, see what's closest to it, and take another point, see what's closest to it, find like the shortest segments and connect them.
Okay, so you're saying that you could be saying a couple different things. One possibility is that you could be saying, I start out, he said, oh, take the short segments and start to do it. So one he says is start someplace and go to the nearest point. And then what would be the next thing you do? Let's say that, let's say we have this and this. What would be the next one that I add by your algorithm?
I would just go with the shortest existing segments in the whole graph, ignoring connecting them.
So you're going to take this one next, right? And maybe you're going to then say, maybe I'll take the next shortest segment. I'll do that one, right? And keep taking the next shortest segment until what would happen? What would happen if, let's say this was the next shortest segment, And let's say this was the next shortest segment. What would I do?
If it's visited twice, you probably would ignore it.
Then I'm going to have to ignore it. Does everybody see what his idea here is? Okay, he's going to take them, he's going to short all there's n points, there's n squared pairs. For every pair there is a distance. Sort the edges from smallest to biggest, that's basically what you're saying. And keep stuffing them in until they cause a contradiction, right? Does everybody get what his algorithm is? Let's look at his algorithm. And let's see an example where bunk, bunk, bunk. That's actually what your algorithm is here, right? It's the closest pair tour, okay? Basically, repeatedly connect the closest pair of points whose connection won't cause a cycle or a three-way branch until all are in the tour. That's basically what you're taking a look at it. Does this always return the correct answer? Can anybody? Probably not, okay? That's a healthy attitude. Does anybody know an example where it doesn't? This may be hard to come up with on the fly, but what's...
You can think of one case where you have a lot of close points and one far point, or let's say like a line of close points and one far point close to the end of one end of the line, then it's a different answer depending on where you start on the line.
Okay. What you're saying is your potential counterexample, and I think this is a healthy thing. It's very healthy to think in terms of counterexamples. You're saying you're going to start saying this is the example that you think is bad, right? And you're going to do what? You're going to, according to his algorithm, what's he going to do? He's going to pick the smallest distance, smallest distance, smallest distance, smallest distance that won't cause a problem. And then once he's finished exhausting all of these, he's got to add this guy in, and that's going to happen here. So actually, on this particular example, I think he might actually get this one right.
But the point is that it depends on which point you start.
Depends where you start. Now, the way he described this algorithm, in fact, up here, we're going to sort the edges as I'm interpreting his algorithm. Again, we have to specify our algorithm precisely, or else we get into these discussions where we're talking about different things. But as I understood his algorithm, he's going to take the smallest, shortest possible segment as the first one and then repeat, okay? So to my understanding of his algorithm, this example didn't break it, okay? There may be other ones, yeah? If I have one row of points, well, okay, if I have equidistant points, and one is, then you're talking about a circle.
Maybe I'm describing it wrong.
Okay, if we're talking about equidistant points that are equidistant and on a circle, that's one possibility. But notice there's a problem. You can't have too many. If this is the radius, what's the circumference of the circle? It's 2 pi r, am I correct about that? Means you can't have too many points there. You can't really build a big example like that. Okay? But actually, I like this. Again, when you go through this exercise, classes do different things. Thinking about counterexamples is a very, very healthy thing. What is my counterexample? I still see some hands, but let me go through my counter. Is this a counterexample or a question?
Actually, I think the first counterexample did disprove it. I just think you kind of did it sideways. If the left of that section were the closest together, then it would proceed to go right on those that close together, and then it would go from the right end all the way to the left end.
This is the one that you're worried about. You're defending this one.
Yeah.
Okay, let me tell you what I think is happening, and then you guys can either argue or we'll do it. I thought the example was a set of points, one far away, and a bunch very, very close to each other on the same line, right? Yeah. And we were now going to keep picking the closest pair of points until... Okay, wait, maybe I see a little bit of a problem here. Okay, so maybe what you're saying is going to happen is we're going to pick the closest point, closest point, closest point, closest point, closest point. This we agree, right? The next closest point I was saying was going to be the one to add was this. Maybe you're saying, oh, this one was the one we would add, right? But obviously, closing off a cycle can't be a good thing to do, right? So usually the way that we would do it is we will keep taking the shortest one until we, until that doesn't cause a fatal problem. A three-way branch would be a fatal problem. A premature cycle would be a fatal problem. If so, then at this point, I believe the heuristic would do this. Okay? Any questions about that? Okay? But what is my counterexample? You guys are right that it's not going to do the right thing. What is my counterexample? My counterexample is to say, let's have two rows of points where they are a little bit closer to each other than they are, the two rows are a little bit closer to each other than they are equally spaced along the row. Does everybody kind of get that idea? So maybe these things are 1 unit apart, and this is 1 minus epsilon apart. What is going to happen if I have 4 of these things where these guys are far away and these are slightly closer? My claim is that the first pairs that are going to get taken are these, because these are the smallest pairs, right? Then the others, the diagonals are all really long. The next smallest ones are going to be the equally spaced things. These things could happen in any order. So let's say I happen to pick these. Actually, let me add another one just to make it end the way I want it to. Okay? Then I claim eventually the only thing that's going to be left is this long diagonal. Well, again, the point I need is a tour, okay? My robot has to come and visit all the spots on the back of my circuit board, right? It has to get back because the robot's got to go do this in cycle. All day it's going to be doing these iPhones, okay? So it does need to be a closed tour, okay? And here every point is touched, but the robot still would have to go back here. Something like that. Okay? So what's the question?
Why couldn't it just do it reverse on the next board?
Okay, so that actually is a good question. So now what you want to say is instead of making a closed tour, what if it could very well in the robot case actually might not need a closed tour. It might settle for an open tour and then do the same thing back and forth. And that for the robot programming thing is probably a perfectly reasonable thing. But for certain cases, you do want closed tours, and that's why I'm dealing with a closed tour. Okay? Any questions? Okay? But what should I like to convince you of? Does everybody agree that this closed tour is shorter than that closed tour? Okay? It's about 22% shorter. Okay? Okay, so that would mean that this algorithm that we talk about isn't right. Yes?
Does this algorithm also fail for open tours?
Does it fail for what?
Open tours?
Would this fail for open tours? The answer is yes. Okay, now can I prove to you it's going to fail for open tours? That's an interesting question. What would be my proof that this fails for open tours? Okay, I'm going to think for a minute. I'm going to tell you the answer is yes, and I know that it does. Okay, let me see if I can convince you of this in just a second. Hold on. It's not happening here. Okay, so the answer is it will fail. Okay, in fact, that's an excellent homework problem for next time. Somebody come in here with an example where it fails for open tours. Yes? What is yours? Okay, give me an example. Work it out offline. Okay, basically, you should be convinced that should be thoroughly convinced it breaks for the closed tour. Okay, you should trust me because I'm not going to tell you the lie that it's going to break for the open tour. But we don't yet have the example that you're going to need. Okay, any questions about that? Let's say, yes, a question back there, or no? Okay, very good. Anything else? Again, another algorithm that people usually give, that because I didn't get, I'm not going to deal with here. Okay, sometimes people say, well, start from a particular point, and then always go to the closest point that is next to it, right? You could kind of imagine like if I was dealing with these, okay? Start from a point and then go to the closest next point, where you always go to visit the closest unvisited point before cycling. That's a natural heuristic. That one is also wrong. And what is the example that I give for this one? Suppose I have points here that are cleverly arranged, a center point to start from, 2 points that are equidistant. If you go in the wrong order, now there's 2 points that are still a distance of 2 apart from each other. If you go in the other direction, you will do that kind of a zigzag thing up top, okay? Whereas the one on the bottom is substantially shorter, where you basically just go all the way from the left to all the way to the right. Yes? Okay, so is this like an elevator problem to service elevators? There are some interesting algorithm routing problems related to what will be the next elevator you send, okay? But it's not clear to me I put this in quite that category, okay? The problem that this category is supposed to be is a problem that you've actually probably heard of. Some of you may have heard of. Have any of you ever heard of the traveling salesman problem? What is the traveling salesman problem? The traveling salesman problem is you have a salesman who has to visit a bunch of cities and get back to where they are. So you got to go to each city to meet the, to visit their customers, okay? And they want to design a route, a trip plan to minimize total travel time. That is a traveling salesman problem, right? In the case of this traveling salesman, the traveling salesman does have a house someplace where he wants to sleep. So the traveling salesman does have to get home, which is why I care about closed tours. Usually people care about closed tours. But the fact that the tour is closed turns out to not be that important a thing. This is why I am comfortable saying this is going to break when you think about it on the open tours. Okay? The problem of finding the shortest tour that visits all of the points, okay, and returns back home is the traveling salesman problem. This is a problem that is known to be NP-complete. It's known to be a hard problem for which there is no fast algorithm. The reason why I know your problem, where you don't have to get back home, is that problem is also a hard problem, okay, an NP-complete problem, meaning that no fast algorithm exists. If this thing worked for, this heuristic worked for that problem, it would be a fast algorithm for a problem that does not have a fast algorithm that exists. Therefore, I know this algorithm doesn't work for your problem. Do you understand my logic?
Yeah.
Okay. But again, the real logic should be construct a counterexample. Okay? Any questions about that? Okay? What is the lesson here that I was hoping is going to get across? The lesson I cared about is that without a proof of correctness, be it formal or whatever you were talking about, an algorithm that does not have an argument as to why it is correct is probably wrong. Okay? And in this case, the heuristics we talked about, visiting the nearest neighbor or constantly taking the shortest non-violating edge, those heuristics will be incorrect. Any questions about it? Okay, and so this is why we care about proofs, and we care about getting the answer there right. Any questions? Okay, so this is going to be a class about algorithms, and one question that I am often asked that's important to kind of resolve quickly is, how do we describe an algorithm? Okay, your job is going to be on homework problems. I will give you an algorithm problem. You will deliver an algorithm. How do you specify the algorithm? Okay? The standard way to do it, there's sort of three ways that this is typically done. One idea is to explain the problem in English. Okay? And explain your algorithm, how you would do it in English. Now, to do that, oh no, what is this thing? Bad news, bad karma. Bad, very bad. Okay, come. No, boom. Okay? Okay. Another idea is to use what we would call pseudocode. Okay, another idea would be to use a programming language. The best way, the most precise way to specify an algorithm is to actually code it up and run it and test it. Okay? In your favorite programming language, be it C, Pascal, Python, or Java, or something like that. Now, the trouble is, it's a lot of work to get a program running. And an algorithm is typically an idea. So implementing the algorithm to sort of describe it is usually overkill, although that is obviously how you get it in a useful format and, and does the job. Usually, often people will use something between English, something called pseudocode, which I picture as being a language that you make up as you write it. It has sort of the operations and the general structure the way a programming language would look. But if you need to at some point describe how to do something tricky in English rather than, describe it, in great detail, that's pseudocode. How do I recommend describing algorithms, particularly on things like homeworks and especially on things like exams? Okay? Algorithms are about ideas. Usually in an algorithm, the idea is best written in English. Okay? There's usually a short, clear idea of what you're trying to do. The detailed steps of what you're doing, probably, if there's some trickiness, should be done in pseudocode. Okay? But even better might be pictures to show what's going on. Again, how did I describe these algorithms to you? Let's take a look at it. The idea of finding the closest bear tour. Okay? In English at top, I wrote a statement in English that was 3 lines long describing what I thought was his algorithm. Okay? The detailed pseudocode looks something like what I have in the black. Okay? For each point, okay, for each step, find the pair of endpoints that are closest and then connect them by an edge. Okay? And keep repeating until there's nothing to connect. Do you see the difference between the relatively clear idea of what is happening in the description English with the messier version in the pseudocode to the even messier version in a program? Any questions? So if I were you to describe the idea, usually the idea is best described in English with pictures to show what you're doing. Okay? Then with details perhaps described in a pseudocode format. Any questions about that? Any other questions about this stuff? Okay. We're now at a point if there's some deep or interesting question. Okay, I'll take it. Yes?
So is it just the difference between a declarative version of the program versus an imperative version of the program?
Okay, so there's some question of, there's different ways of writing algorithms. By, you say, declarative and imperative, I am going to reinterpret that as saying you could do it recursively, or a functional recursive kind of thing, or an iterative thing with loops. Any way you write the algorithm is fine. So you sort of express what the idea is. Okay? Different ways of expressing the algorithm might make it easier to analyze or not analyze, just basically in terms of understanding how it works. But we'll talk more about analysis next class. Any questions? Okay. The class ends what, at 2:10? Or is it 2:20? 2:20, very good. Okay, I'm glad. Okay, then I won't stall, and I'll go to the next thing. Okay, good. Any question about the traveling salesman problem? Okay. Let's go through and now try another one of these algorithm warm-up exercises. which is a somewhat less familiar problem than the traveling salesman problem. But it's an interesting one. It's something that I would call the movie star scheduling problem. It has to do with the following situation. Suppose, let's say, you are a movie star or an agent for a movie star, and you're trying to pick between which roles a movie star should take. The x-axis here represents the calendar, okay? That this is over here is the beginning of the year. Here is the end of the year, okay? Every possible movie job that's being offered to you is going to want you to commit for the entire period. So you can only take one possible job at a time, okay? You are paid $1 million per movie, okay? So your goal is to naturally, being a great artist like yourself, you want to get as many movies as you can so you can get paid the most, okay? So the question is the following. How would we figure out, given a set of possible jobs here, what are the biggest number of jobs you can take that won't interfere with each other? Do you see what the problem is? You are forced to decide, should you work on calculated bets or process terminated? Okay, you can't be in both of those movies because they need you at the same time. Does everybody have that idea yet?
Just to clarify, this isn't asking for the movie star to be occupied for a maximum amount of time. It's a maximum number of roles.
Right, so here I don't want the movie star to work, it's the maximum number of roles. You get paid $1 million per movie. Okay, it doesn't matter if it's a short movie, it doesn't matter if it's a long movie. If they'll give it to you for a commercial, that's great. Okay? But our goal here is to find what is the maximum number of jobs that you can take. In this particular case, what's the maximum number of movies that somebody can take? 4. Okay, someone with a hand. Tell me which 4 movies. Yes. Discrete mathematics, right? Halting state? Okay. Programming challenges? And then calculated bets. Does everybody see that this person can do 4 movies? Okay, but there's no way for them to do 5 movies. Okay? Any questions? So as the agent for these people, if I give you a bunch of intervals representing jobs, how do I find the largest set of non-intersecting intervals? Does everybody see what the problem is here? Okay? Does anybody have an idea of a way to do it? Okay, here's a new hand. Okay, well, you.
Maybe start with the movie that has the shortest length of time needed plus the fewest amount of overlap with it.
Okay, so let's think about it. So first you say start with the one with the fewest amount of time needed and the the fewest overlaps to it. Okay? Now that's 2 different things, and to make that a rigorous algorithm, you probably have to state exactly what the condition is for picking that. Okay? Let me say what I would have wanted you to say. Maybe you said pick the one that is shortest, the shortest job. Let's forget about the overlaps. That's not quite what you said. If we pick the shortest possible job first, is that going to give us the best possible answer? Okay. Who here says no? Who has an example? Okay. What would be an example? You. You, yeah. Okay. Okay, so do we have a particular counterexample here that we can do? A quick, insightful, bam, convince me otherwise. Yes?
Okay, 2 long ones don't overlap each other, and 1 short one, 3
Does everybody see that if we have a world where you're saying, oh great, I've got that beer commercial to do. Here there are 2 long jobs that, okay, by taking the beer commercial, you can't do War and Peace 1 or War and Peace 2. Does everybody see that? Okay? So just picking the shortest job isn't going to be doing it. Okay? Any other ideas for how we might do this one? Okay, let's try you. Okay, yeah, you.
You can start by modeling each interval as a start time and end time, and then just try and like progress forward, but not like
Okay, don't know, then when I hear I don't know, that's when I'm stopping. Okay, let's try another one. Let's try you.
Picking the movies that end first.
Okay,
Remove all the overlaps.
so let's think about this one. This is an interesting one, okay? Let's take a look at it. So first of all, let's just take a look at what the one thing to do. You say pick the one that ends first. What about picking the one that starts first? Is picking the one that starts first a good idea? Okay. So what would be an argument that picking the one that starts first isn't going to lead to the right answer? Okay, yeah? What would be not you, next one, you next. Does everybody see that if you start first, okay, if you had War and Peace might have been the first movie. Picking the first job, okay, would have been a disastrous thing to do, right? But that was not really the idea. Okay, any questions? Okay? Any other ideas here about what might be good? Although we have a good idea on the table. In fact, let's look at the idea on the table, because that's one that actually is going to do the right thing. Okay? What about a job where the idea is to pick the first movie, do the movie with the earliest completion date, okay? And then pick delete anything that intersected it, and then do the next one with the earliest completion date, okay? Let's look at this for a second. I want to make sure we understand what the algorithm is first. Let's go back to our book problem. Which is the movie with the earliest completion date? Discrete math. I'm going to do that. And now I can't do this one. I can't do Tarzan of the Jungle. What is the next one with the next earliest completion date? Halting state. I'm going to do halting state. Okay? And what is my next one? I can't do Steiner's tree. What is the next one that's going to have the earliest completion date? Programming challenges. Does everybody see that? Okay, and then after that, what's the next one that has the earliest completion date that didn't overlap this? Calculated bets. Does everybody see on this example, picking the earliest completion date does the right thing, yeah?
Would it be safe to go backwards and just always pick the one that starts last?
Well, let's first see if it's safe to do this before we hold that or hold that for a second. Let's see where we are now. Does everybody see what the strategy is? Pick the earliest one to complete first, okay? Why is this one right or wrong? Can anybody give me a counterexample? Or can anybody argue that this is the right thing to do? Does it pay to pick the first one to complete? Okay, just to mix it up a little bit. Anybody else have an idea? Okay, you.
Maybe you could do an inductive proof that says, because if you pick the one that has the earliest completion date, then you just get one out of the way, and then you have to just prove with the remaining movies that are left that it's the way, and then if you only have one movie.
Okay, we're getting this idea, this whiff of an inductive idea. Okay, yeah?
I don't think you can do it really inductively, though, because when you select a particular job to take, you're deleting some other jobs. And so
Okay, so the question of how do you do the inductive thing, yeah?
If we pick the first time, like the first movie ends there, we're deleting the movies overlapping and we delete the least most, the movies.
You're saying you're deleting the least amount of badness, okay? Again, I will say that this is a proof. I would say that there is a proof by contradiction is the magic word that I would be using here, okay? Computer scientists only know two ways of proving things. They can prove things by induction or they can prove things by contradiction, okay? And what is the idea here? The idea here that I like is I think the idea that he had. Suppose we don't, in a contradiction, we're basically arguing that suppose we didn't prove that something bad happens. That's kind of what happens in a proof by contradiction. But his observation, let's say before it was, let's say that these were the first movies that we had. Okay? The algorithm is going to be saying, pick this one, because this is the first one to end. Okay? Now, the claim is that we're going to be better off, at least as well off, than if we had picked any one of these other movies, right? Why, could we have possibly been better off picking this movie rather than this one? The answer should be no. Why is it? Because there is possibly another job here that we would like to be able to take, that we can take if we took this movie, but not this one. Does everybody see that any movie, if this is the first one that ends, then it eliminates the fewest number of possibilities. Does everybody see that? Okay? And so if you give me a solution, you tell me, no, the winning solution had this movie and not this movie. Is it clear that I could remove that from your assignment, put this one in, and it would be just as good? Right? Any solution, if there was a way of doing it with 4 movies, picking this one, or this one, or this one, there would be a way to do it with 4 movies, dropping this one, or this one, or this one, and putting it in. Right? You can't hurt yourself picking this one instead of any of the other ones, right? How do we know that we're going to pick any one of these? How do we know maybe this was the first movie we worked on? Okay? How do we know that's not the case? Okay, yeah? If this was my first movie I actually had in my solution, I could have had an even better solution by including that one as well, right? Does everybody see that? Yeah.
Would there be another way that you would have to put in to determine if 2 movies ended at the same exact time?
So what would I do if 2 movies ended at the exact same time? Which movie would I want to take? Well, the shorter one only because you're a lazy cuss, right? Is there any, but I mean, from a point of view of maximizing the number of movies, does it make any difference? The answer is it does not, right? It could very well have been one of these was all the way back here, right? Does everybody see here that there's kind of this, the idea here is the idea about not blocking it, right? And the formal proof of this thing has to do with basically thinking about a proof by contradiction, where you argue with me, saying, no. Here, I say that there exists a case where this is wrong. This was an instance where these were the optimum number of movies, and there was another one here. Okay? I said, no, I could have removed this one, put this one here, and the solution would have been quiet, at least as good as that. Any questions about that? Yes? So how would I do this one? For correctness, I am going to want to do this thing by always taking the first one that ends. I would probably sort the movies by what was their ending time, right? I would pick this one, okay, pick the first one that's there, then delete every one that, go through the rest of them and saying, does it overlap this? Delete it. Does it overlap it? Delete it. Does it not overlap it? Take it. And so basically the time of this is going to be the time it takes to sort it and sweep it. Any questions about that? Okay, so in your life, what is the lesson here? Looking for counterexamples is the important thing that we're going to learn how to do. Okay, or you're going to learn how to do between now and the next class, because the daily problem is on this thing. How do we look for counterexamples? We think about small examples. Notice that one of the counterexamples had only 3 segments in it. We think about examples with ties because that makes it trickier, and maybe the algorithm's going to do something stupid with ties. And we think about contrasts of big and small. Think about it next class for the daily problems on something, finding a counterexample. Good luck. I'll see you next class.